Good afternoon, everyone. So we'll be beginning with the new chapter, that is the electrostatics, right? We'll be starting with the electrostatics part 1, right? For NEET 2024, right? It's a pure revision series with respect to your NEET 2024 uh, that's going to commence on 5th of May 2024, right? So we'll be beginning with the chapter. We have already finished the current electricity into two parts, right? Part 1 and part 2, right? You can watch those two parts as well, right? Now let's start with the electrostatics part, right? From this chapter, there are at least 3 to 4 questions are asked from this chapter every year, right? So we'll be focusing on this chapter, right? Into 2 or 3 parts, right? So let's begin with the electrostatics part 1, right? So beginning with the question number one, you can see here on the screen. The question number one says that which of the following charges is or are not possible, right? So we have been given 4 charges here in options, right? Option number 1, 3e, and option number 2, right? That's 48 into 10 to the power minus 19 coulomb. Then option number 3, that's 3.2 into 10 to the power minus 20 coulombs, right? Then we are left with the option number 4, that's 1 coulomb, right? So the question is that which of the following charge is not possible. We know that according to the quantization of charge, right? The concept of the quantization of charge comes into play here, right? We know charge is a quantized quantity, right? It means that the charge that is possible to have q, that's equal to integral multiple of charge of electron, right? That's Ne, right? So q is equal to Ne, right? So it means that we can have the 1 electronic charge, 2 electronic charge, 3 electronic charge. We cannot have 1.5 electronic charge, 2.5 electronic charge, right? And so on, right? So we'll begin with this, right? The value n should be a natural number here, right? N should be a natural number here. So n is equal to q upon e, right? The option where we get the n equal to natural number, then that will be the correct option, right? So you can see here for the first option, q is equal to 3 times e, so 3e upon e, that's equal to 3, right? So it's a possible charge, right? It's a possible charge, but we have to find the charge which is not possible, right? Now talking about the option number 2, right? Option number 2, the value of n will be equal to 48 into 10 to the power minus 19, right? Upon charge of electron, that's 1.6 into 10 to the power minus 19, right? This and this will be cancelled, right? We'll be left with 48 upon 1.6, right? If you multiply it by 10 and divide by 10 as well, right? It will be 480 upon 16, right? 480 upon 16. So it will be 16 into 3, right? 16 into 3 is 48, right? 16 into 3 is 48. So it will be 30, right? So 30. So the value of n comes out to be equal to 30. So this is also a possible charge, right? Now talking about the charge 1 coulomb, option number 4, right? Option number 4, right? So n value here will be equal to 1 upon the charge of electron, that's 1.6 into 10 to the power minus 19 coulombs, right? So from here you can see the possible value of n will be equal to 6.25, right? It will be equal to into 10 to the power minus 19, right? 10 to the power minus 18, right? So this is also a possible charge, right? It's also a possible charge, right? 6.25 into 10 to the power minus 18, right? It means these number of electrons for 1 coulomb of charge, we can plus 18, not minus 18, it should be plus 18. So 6.25 into 10 to the power 18, right? Or we can write it as 625 into 10 to the power 16, right? We can see here the value n is once again a natural number here, right? It means this is also a possible charge. This is also a possible charge, right? This is also a possible charge. Now talking about the option number 3, right? For the option number 3, the value of n will be nothing. It will be 3.2. 3.2 into 10 to the power minus 20 upon 1.6, right? Into 10 to the power minus 19, right? Now from here, it will be 2, right? It will be 2 and it will be left with 2 into 10 to the power minus 1, right? So from here, the value of n comes out to be equal to 0.2, right? So this 0.2 is not a possible, right? Because n should be a natural number, right? The value of n should be a natural number, right? It can be 1, 2, 3, 4, 5. It cannot be a fraction. It cannot be a 0.2. It cannot be 0.5. It cannot be 1.5. It cannot be 2.7, right? So the correct option for this question is option number 3 is the correct option. This charge is not a possible charge, right? So option number 3 is the correct option for this particular question. So what we did in this question is we used the quantization of charge. According to quantization of charge, the total charge can be equal to n times the charge of electron, right? So that's why we say that n should be a natural number, or we can say the charge is a quantized quantity, right? So option 1, 2, 4 are possible charge, but option number 3 is not a possible charge. So the correct option for this question will be option number 3, right? Now let's move on to the question number 2, right? Moving on to the question number 2, find final charge on the spheres when switch S is closed, right? We have been given two spheres here, right? Two spheres of different radii, right? Now we have to calculate the final charge, right? Final charge when switch S is closed, right? Let's suppose there are these are two spheres. One sphere is of radius 2 centimeter, and the sphere is radius of 3 centimeter, right? There's a charge of 60 microcoulomb on this sphere, right? 60 microcoulomb charge on this sphere and minus 100 microcoulomb on this sphere, right? So the two charges are there on this sphere. One on first sphere, the charge is 60 microcoulomb, and on the second sphere, the charge is minus 100 microcoulomb, right? Now, when the switch S is closed, right? When the switch S is closed, right? When switch S is closed, then there will be a redistribution of the charge, right? Redistribution of the charge will take place, but the total charge will be always conserved. So the total Q total has to be equal to minus 40 microcoulomb, right? Minus 40 microcoulomb, right? Now you can see here, this is the total charge, right? This is total charge, that's minus 40 microcoulomb. The redistribution of the charge will take place according to the radius of these spheres, right? So this charge will be directly proportional to the radius of the sphere, right? This charge will be directly proportional to the radius of sphere, or we can say Q1 upon Q2 will be equal to R1 upon R2, right? R1 upon R2, right? And once the distribution takes place, the final charge will be Q1 upon Q2. It will be equal to R1 upon R2, or we can say the Q1 will be nothing. It will be total charge multiplied by R1 upon R1 plus R2, right? R1 plus R2. So this will be Q1, right? Now the total charge is nothing, that's minus 40 microcoulomb, and the value of R1 is 2 and the value of R2 is 3. It will be upon 5, right? 5 into 8 will be 40, right? It will be 16, right? So Q1 will have this value equal to minus 16 microcoulombs, right? Minus 16. If this has the value of minus 16 microcoulombs, right? Minus 16 microcoulombs, we have total charge equal to minus 40 microcoulombs. It means the final charge on the sphere, second sphere, will be nothing. It will be minus 24 microcoulombs, right? It will be minus 24 microcoulombs. The value of Q2 comes out to be equal to minus 24 microcoulombs, right? So this will be the this is how the charge distribution will take place in case of two spheres. In case of two spheres having different radii, the charge distribution will take place according to the radius of the spheres, right? And Q will be proportional to R, and Q1 by Q2 will be equal to R1 by R2. This is how the charge distribution will take place, right, between the two spheres. Now let's move on to the question number 3, right? Moving on to the question number 3, you can see here the question number 3 says that uh, the device which is used to detect presence of charge, right? Uh, the device used to detect presence of charge is, right? We know that option number 1 says that ammeter. Ammeter is a device used to measure the current, right? It's a device used to measure a current, right? And we have Van de Graaff generator, right? Van de Graaff generator is actually used to a Van de Graaff generator is actually used to create a large electric field on on a conductor, right? Then by meter bridge, it's used to calculate the unknown resistance. The correct option here is gold leaf electroscope. It's the gold leaf electroscope which is used to detect the presence of charge in any object, right? So the gold leaf electroscope will be the correct option for this question, right? So gold leaf electroscope is a device which is used to detect the presence of a charge, right? Now moving on to the question number 4, right? The question number 4 says that force between two identical spheres, right? We have two spheres given A and B carrying same charge, right? And separated by a distance r in vacuum is F. So it means that we have two spheres, right? We have two spheres A and B, right? This is sphere A, right? This is sphere A, and this is sphere B, right? There are two spheres, sphere A and sphere B, right? carrying same charge. If the charge on sphere A is q, then the charge of sphere B is also q, right? And they are separated by a distance of r, right? They are separated by a distance of r, right? The separation between the two spheres is r, right? And the force between these two spheres is given as it's given that the force between the two spheres is F, right? Force between the two spheres is F. A third identical sphere C, right? There is a third identical sphere, right? C, which is brought. There is a third identical sphere C, right, which is brought in contact with A, then B, and finally C is taken away, right? So first of all, this third sphere, right? Third sphere, identical sphere, right? If this sphere is identical, right? Or we can say that let's suppose the charge on the sphere is once again q, right? It's identical, right? It's brought in contact with this sphere, right? It's brought in contact with this sphere, right? The charge on the sphere is not given, right? And the radius of this sphere is once again r, because they are identical spheres, right? Once this sphere C is brought in contact with sphere A, there will be charge redistribution, right? Since they are identical spheres, right? So the final charge on each of this sphere will be nothing. That will be given by q1 upon q2 upon 2, right? This will be the distribution only in case the two spheres are identical, right? For identical spheres, right? For identical spheres, this will be the final charge on both the spheres, right? It means that when this sphere and this sphere are brought in contact with each other, then the final charge on sphere A will be q by 2, right? Q plus q q q plus 0 upon 2, it will be q by 2, right? The charge on this will be q by 2. This is sphere A, and the charge on sphere C will also become q by 2, right? Now, this third C is now again brought in contact with sphere B. It's again now brought in contact with sphere B, right? Now, once again, the charge distribution will take place according to Q1 upon Q2, Q1 plus Q2 upon 2, right? It means that finally the charge on sphere B will be Q plus Q by 2 upon 2. That will be 3Q upon 4, right? 3Q upon 4 on this sphere, right? And the charge of finally C will also have a 3Q upon 4 charge, right? Now the question is that now force between A and B becomes, right? Now there are two spheres now separated by the same distance, right? A and B, right? A is having the charge Q by 2, right? And the B is having the charge of 3Q by 4, right? 3Q by 4. We have to find the force separated by the same distance, right? Separated by the same distance R, right? Now the force between them will be F is equal to K q1 q2, right? That will be q upon 2 multiplied by 3q upon 4, right? Upon r square, right? That will be equal to 3kq square upon 8r square, right? This is the force. Now initially the force was nothing. That was equal to F is equal to kq square upon r, right? Kq square upon r square. This was the force. Now the kq square r square we can replace with F, right? So the final force between these two spheres, right, will be 3 times F upon 8, right? So this will be the final force between all three spheres. This will be the final force between A and B, right? So the charge distribution takes place when the two spheres or the two metallic bodies are brought in contact with each other, right? If they are identical spheres, then the charge distribution will take place, or the final charge on both the spheres or both the conductors will be Q1 plus Q2 upon 2, right? This was for the identical spheres, right? But if the spheres are not identical, the charge distribution will take place according to their radius. That's Q will be proportional to R, or Q1 upon Q2 will be R1 upon R2. This is how the charge distribution will take place in spheres, right? Now, moving on to the question number 5, right? Let's discuss question number 5. The question number 5 says that a particle of mass m carrying charge q1 is revolving around a fixed charge, right? q2 in a circular path of radius r. Calculate the time period of revolution and its speed also, right? It means that we have two charges. We have two charges here, right? We have two charges q2, and there's another charge q1, right? There is another charge q1, right? There are two charges q2 and q1, right? Like this. The q2 is at the center, right? The q2 is at the center, right? And the q1 is revolving in a circular path, right? The q1 is revolving in a circular path, right? Of radius r, right? Of radius r. of radius r. We have to calculate the time period of revolution, right? And its speed also, right? Its speed also. Now you can see here, uh, the speed of this, we know the necessary force for this charge q1 to move in a circular path is provided by the, it's equal to the centripetal force, right? That's what we call a centripetal force, right? It's always along the radius of the circle and towards the center of the circle, right? Along the radius towards the center, right? Now the question is that the necessary centripetal force here in this case will be provided by the electrostatic force of attraction between Q1 and Q2, right? The electrostatic force of attraction between Q1 and Q2 is KQ1 Q2 upon R square, right? This should be equal to the centripetal force, right? That's mv square upon R, right? R and R will get cancelled. From here, the value of speed comes out to be under root of KQ1 Q2, right? Upon M, right? M into R, right? This will be the speed of this particle moving in a circular path because of the mutual force of attraction between Q1 and Q2, right? So one of the charge should be a positive charge, another charge should be a negative charge. Then only this circular path is possible. Attractive force should be there, right? Otherwise, there will be a repulsive force. The circular path will not be possible in this case, right? Now talking about the time period of revolution. So time period will be nothing. It will be the total circumference of this circle. That's 2 pi r upon the speed of this charge, right? So 2 pi r upon v, right? V is nothing. That's under root of k q1 q2 upon m into r. So this will be the time period, right? This is nothing. This is the time period. So this is the time taken by this charge to complete one complete revolution, right? One complete revolution. That's what we call as the time period for this charge Q1, right? Now, let's move on to the question number 6, right? The question number 6 says that find the value of charge, right? The question number 6 says that find the value of charge placed at the center of given system, right? So that the system remains in equilibrium. Now we are discussing the questions of equilibrium, right? We have three charges placed at the corners of a equilateral triangle, right? Each of charge Q, Q, and Q, right? The side of the triangle is A, right? And we have to place a charge at the center of the given system, or we have to place a charge at the centroid of this triangle, right? Such that the system will remain in equilibrium, right? Let's first of all see whether the system is in equilibrium before placing a charge or not, right? Let's assume that this is the point C here, right? This is A and this is B, right? Let's talk about the equilibrium of this charge placed at point C, right? Let's talk about the equilibrium of charge placed at point C. The force on this charge Q will be because of the two charges placed at A and second charge placed at B, right? So it will be a repulsive force because all the three charges are positively charged, right? It will be a repulsive force. The force of repulsion because of the charge at A will be along this direction. Let me call this as F1. That will be equal to KQ square upon A square, right? And the force because of charge placed at P will be along this direction. It will be a repulsive force. This will be F2, and it will be equal to, once again, KQ square upon the distance square. That's A square, because each of the side of this triangle is A. It's an equilateral triangle, right? So for equilateral triangle, we know that each angle here is 60 degree, right? And the total sum of all the angles is 180, right? Each angle is 60 degree, right? If this is 60, this has to be equal to 60, right? This has to be equal to 60, right? This has to be equal to 60. So before placing the charge at centroid, the net force on this charge Q will be, Q will be, that's equal to, if the two equal force are acting at a point, but with the same magnitude, the equivalent force or the net force is given by F net is given by 2F cos theta upon 2, right? 2F cos theta upon 2, right? So we can replace F with one of the magnitudes, that's KQ square upon A square, and the angle between here, the two forces, is 60 degrees. So it will be cos 60 upon 2, that's cos 30 degree, right? Cos 30 degree. So from here, it will be 2KQ square upon A square. Cos 30 degrees, nothing. It's equal to root 3 over 2, right? Root 3 over 2. So we'll get the answer root 3 KQ square, right? Root 3 KQ square upon A square, right? This will be the net force. This will be the net force. Net force on. This will be the net force on this particle, right? On this charge Q placed at C. On this charge Q placed at C. Now, we have to place this charge Q at C in equilibrium. So it means there should be equal amount of force in the opposite direction, right? Equal amount of force in opposite direction, right? That's root 3 kq square upon a square on this charge Q. Then only it can remain in equilibrium. Then only it can remain in equilibrium because there is a net force along this direction, right? Equal to root 3 kq square upon a square. There should be an equal and opposite force on this charge Q at C so that it remains in equilibrium. So the only force that is possible, the only force that is possible right here, that will be because of the charge placed at the centroid, and this charge must be a negative charge. This charge must be a negative charge because the force must be attractive. Only then it will remain at equilibrium. So this charge must be a negative charge, right? This charge must be a negative charge, right? Now we have to calculate the magnitude of this charge, right? We have to calculate the magnitude of this charge. So the force here will be equal to, the magnitude of the force will be here equal to kq q upon the distance between the center and centroid and one of the corner is nothing. It's a upon root 3, right? It's a upon root 3. It's a distance between the centroid of a triangle and one of the corner. That's a upon root 3. So kq q upon a by root 3 whole square, right? This must be balanced by this force, right? Root 3 kq square upon a square, right? They should be equal, right? So from here, k and k will get cancelled, q and q will get cancelled, right? So we'll be left with, so it will be root 3, it will be 3q upon a square. That has to be equal to root 3. We'll be left with q here upon a square, right? Now a square and a square will get cancelled. So the value of q comes out to be equal to root 3 q upon 3, right? Or it will be equal to, q upon root 3, right? Q upon root 3. So this should be the magnitude of the charge, or we can say the charge to be placed at this point should be equal to minus q upon root 3, right? So this should be the charge placed at the centroid, right? That's minus q upon root 3 at the centroid, so that the charge placed at C will remain in equilibrium, right? Charge placed at C will remain in equilibrium, right? So this is how the equilibrium is possible, right? Now let's discuss the question number 7 here. In the system of two charges Q and 4Q, right? In a system, in this system we have two charges, each of q and another charge of 4q, right? Where should be third charge must be placed so that net force on the third charge will be 0, right? So it means that in between these charges q and 4q we're placing some charge q, right, at some distance. Let's suppose we're placing at a distance of x from the charge q, right? The total distance is 2a, so the distance from here to here will be equal to 2a minus x, right? 2a minus x. We have to place the charge q in that position so that the net force on this charge is 0. It means that there will be two forces on this charge, right? There will be two forces on this charge. This charge q can be a negative charge. It can be a positive charge as well, right? If this charge is a positive charge, this charge will repel along this direction. This charge will repel along this direction, right? So it can remain in equilibrium. And for the if this charge is a negative charge, then this charge will be attracted towards this, and this charge will also be attracted towards 4q. So once again it can remain in equilibrium. Let's suppose the charge is q, right? The charge is q, and we have to find the distance x at which it will remain at equilibrium, right? So the net force on this charge should be equal to 0, right? It should be equal to 0. Let's suppose the force because of q is along this direction, that's f1, and because of 4q is along this direction, that's f2, right? So this f1 must be equal to f2, then only it will remain in equilibrium, right? The value of f1 here will be nothing, that f1 will be equal to, it will be kq into q upon x square, right? The value of f2 will be equal to, k q into 4q, right, upon the distance square, that's 2a minus x whole square, right? X whole square, right? And these two forces should be equal, right? For the charge q to have net force equal to 0, right? So q upon x square will be equal to 4 times kq square upon 2a minus x ka whole square, right? Now from here k and k will get cancelled, q and q will get cancelled, right? Okay. The third charge, the value of the third charge is not given here, right? So we have to find this x, right? We have to find this x, right? So from here, q upon x square comes out to be equal to 4 q upon 2a minus x whole square, right? 2a minus x whole square, right? So what we can do here is that q upon 4q, right? Q upon 4q will be equal to x upon 2a minus x whole square, right? Right? So, or we can say that 4q upon q will be equal to 2a upon x, right? Minus 1 whole square, right? Where to find the value of x? So it will be root 4 capital Q upon Q, right? That will be equal to 2a minus 2a upon x minus 1, right? Or the value of x here will be, that's 2a upon x will be equal to 1 plus 2 root q upon q, right? Right? So from here, the value of x will come out to be equal to, the value of x will come out to be equal to, it will be x will be equal to 2a, right? 2a upon 1 plus 2 times root q upon q, right? Root q upon q, right? So this will be the value of x here, right? This will be the value of x. Now let's suppose if the charge q is equal to capital Q, right? If the charge q is equal to capital Q, then the value of x will be 2a upon 1 plus, right? 1 plus q upon q, right? It will be 2, right? That will be equal to 2a upon 3, right? 2a upon 3. The value of x will be 2a upon 3, right? Let's discuss the question number 8 here, right? Now discussing the question number 8 here, right? Discussing the question number 8 here, right? You can see in the question number 8, we have two charts, each of magnitude q are fixed at distance 2a, right? At a 2a distance apart, right? There are two charts, right? Each of q, right? Each of q, they are fixed at a distance of 2a apart, right? 2a apart. A third charge of minus q charge, right, of mass m is placed at the midpoint. There is another third charge which is of charge minus q and mass m, right? And mass m. It's placed at the midpoint, right, of the two charges. When the charge q is slightly displaced perpendicular, it means that if we slightly displace this charge minus q, right, by a displacement of x, right, in the perpendicular direction, right, then find its time period. Right? We have to find the time period, right? Now you can see if it displaces this charge q by distance minus x, right, at this point. Now there will be two forces on this charge. One force will be the attractive force because of this charge. Another force will be attractive force because of this charge, right? Now let's suppose the displacement here is x in the upward direction, right? It's x in the upward direction, right? The value, the distance from here to here is a, the distance from here to here is a, right? Then the value of this r will be equal to, it will be nothing, it will be under root of a square plus x square, right? And this r will be once again equal to under root of a square plus x square, right? Now both the forces will be attractive forces here, right? Both the forces here will be attractive force here, right? Both the forces will be attractive forces here, right? Now let's suppose the angle between the two forces is actually theta, right? If theta is the angle between the two forces, right? If theta is the angle between the two forces, right? If theta is the angle between the two forces, this angle is theta here, right? Then this should be theta by 2, right? And this should be theta by 2, right? This should be theta by 2. Now what we can do here, we will find the net force on this charge, right? So the net force, let me call this force as F1 and this force is also F2, right? F2. So we can see here that the net force here will be F1 is equal to, that's K Q Q upon distance square, right? Upon distance square, that's a square plus x square, right? And the value of F2 will also be equal to K Q Q upon the distance square, that will be a square plus x square, right? Now these are the two forces of equal magnitude but at an angle of theta, right? So the net force will be nothing. That will be given by 2f cos theta upon 2, right? 2f cos theta upon 2, right? Now the value of f is 2 times k q q upon a square plus x square, right? X square, right? A square plus x square and the factor cos theta by 2. Now we know this angle here is theta by 2. So the cos theta by 2 where here will be, it will be x upon that's base upon hypotenuse, that's x upon under root of a square plus x square, right? A square plus x square, right? So from here we get the value 2k q x upon under root of that's a square plus x square raised to power 3 by 2, right? That's the net force, and this is an attractive force, right? This is an attractive force. So we can put a negative sign here because of the attractive nature of these two forces, right? It means that this is the net force, right? Now this displacement is a very small displacement, right? Or we can say x square is much less than a square, right? We can neglect x square as compared to the a square. So the net force here will be minus 2k q into q, right? X upon under root of a square multiplied by 3 by 2, right? 2 and 2 will get cancelled. We'll be left with 2k q x upon a cube, right? Now you can see this actually represents the equation of simple harmonic motion, right? That's minus alpha x, right? Minus alpha x. Where the time period is given by t is equal to 2 pi under root of m upon alpha, right? M upon alpha. This is the time period of the simple harmonic motion. In case of simple harmonic motion, the force is directly proportional to the negative x, right? That's what it follows here, right? So from here, the time period will be nothing. Time period will be 2 pi under root of m upon alpha. The value of alpha comes out to be equal to alpha is nothing. That's equal to 2k q upon a cube, right? So value of alpha is this. So we can replace it with 2k upon a cube, right? So this is the value of alpha. So time period comes out to be equal to 2 pi under root of m a cube, right, upon 2 times k small k q multiplied with the capital Q. So this will be the time period of oscillation for this charge minus q, which will be oscillating about this point, right, where it was placed initially, because at this point the net force on this charge is zero, or we can say this is a point of equilibrium, right? Now discussing about the question number 9, right? Let's move on to the question number 9, right? So the question number 9, according to the question number 9, you can see here, calculate the electric field at origin, right? Due to infinite number of charges as shown in the figure A and B, right? We have two figures here. We have to calculate the electric field, net electric field at the origin because of this infinite charge distribution, right? Because of this infinite charge distribution, right? Now let's talk about the case first, right? Case A. Now you can see here there will be a electrostatic field because of this Q, and so on up to infinity, right? We can and all the fields will be along this direction because of the positive charge, right? Now we can it means the total field will be the algebraic sum of each and every field because of all these charges, right? So the net field will be E net will be nothing. It will be KQ upon distance square, that will be 1 square, right? It will be KQ upon 2 square, right? It will be plus kq upon 4 square, right? And so on, right? This will be the net field, right? Now if we take kq as common, we'll be left with 1 upon 1 square, right? Plus that will be 1, that will be 1 upon 4, that will be 1 upon 16, right? And so on, right? And so on, right? You can see that this is a equation of what we call as the net electric field at the origin or point O is kq, uh, and this summation and this series, right? This series, right? So it means that we have to find the sum of this series, right? To calculate the net field at the point O. To calculate the net field at the point O, right? So the net field at the point O has to be the sum of this series, right? You can see that, look at this series, that's 1 plus 1 upon 4 plus 1 upon 16, right? 1 upon 16 plus so on. If you calculate the common ratio here, the common ratio comes out to be equal to 1 upon 4, right? The common ratio comes out to be equal to 1 upon 4, and the first term here is equal to 1, right? So it is an infinite sum of GP series, right? It follows a GP, right? It follows a GP here, right? And we know the sum of infinite series in case of GP, it's nothing. It's equal to A upon 1 minus R, where A is the first term. The first term here is 1, and this common ratio here is 1 by 4, right? So it will be equal to 4 upon 3, right? It will be equal to 4 upon 3. So the net force, a net field at the origin in the case first is nothing. That will be 4 times kq upon 3, right? This will be the net field at the origin, right? So this is the net field at the origin because of this charge, infinite charge distribution, right? Net field at the origin, right? Now let's discuss the part B of this question, right? Discussing the part B of this question. I can see we have the charge alternate positive and negative charge now placed along this x-axis with the infinite charge distribution once again, right? We have to find the electric field at this origin O. Once again, the net field will be the because of this plus q and then minus q, then again plus q, then minus q, right? So because of this plus q charge, the field will be along this direction, and because of this negative charge, the field will be along this direction. So it will be kq upon 1 square, right, minus kq upon 2 square, right, plus kq upon 4 square, right, and so on, right, and so on. So this will be the infinite sum of charge here, right? Infinite sum of electric field, right? Or we can say the net field here will be equal to, that will be equal to kq into 1 minus 1 upon 4 plus 1 upon 16, right? And so on, right? And so on, right? So this will be the, once again, the infinite sum of series, right? Infinite sum of series, right? You can see here if we calculate the common ratio here, right? The common ratio here will be equal to minus 1 upon 4, right? The common ratio here will be equal to minus 1 upon 4. So ratio is nothing, that's minus 1 upon 4. And the first term in this case is equal to 1, right? It's once again a GP, right? It's a geometric progression, right? The sum of infinite series in GP is nothing, that's A upon 1 minus R, right? So the net field here will be equal to KQ, right? First term is here 1, and common ratio here is minus 1 upon 4, right? So we'll get here the value equal to, it will be 4 upon 5, right? It will be 4 upon 5. 4 kq upon 5, right? This will be the net field at the origin O, right? In the case second, in the part second, right? It's a very important question, right? With respect to a NEET, upcoming NEET exam, right? Very important question, right? For calculating the potential or calculating the field due to the infinite charge distribution placed on the x-axis, right? Now let's look at the question number 10, right? Let's look at the question number 10. The question number 10 says that four identical charges are placed on the corners of a regular pentagon. Find the electric field at the center of the pentagon, right? There are four regular charges, identical charges placed at the corners of a regular pentagon. And we have to find the electric field at center of the pentagon. So at the center of this pentagon, we have to find the electric field, right? We have to find the electric field. Now you can see here there are four charges Q, 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 and Q, right, placed at the four corners of this pentagon, right? And we know one important property, that if n identical charge is placed at n corners of a regular regular polygon, right? If n charge are placed, if n charge are placed, n charge are placed at n corners of regular polygon, right? Regular polygon. So all these charges should be identical, right? All these charges should be identical. They should be identical charges. They should be identical charge, right? The net field at the center, net field at the center is always equal to 0. The net field at the center is equal to 0, right? So the net field at the center will be equal to 0. Now, but in this case, you can see there are five corners, but only four charges are placed at the corners of the at the four corners of this pentagon, right? But we can do what we have to calculate is the field at center. Now, in this case, the field will be non-zero field because only four charges are placed, right? Not all the five charges are placed on the five corners, so the field will not be zero here. Field will be a non-zero. So how can we find the field here? What we'll do here is that we will add a charge of plus q at this corner and add a charge of minus q at this corner, right? I can see here because of this plus q, plus q, plus q, plus q, plus q, these are the five charges placed at the five corners of the polygon. Because of these five charges, the field will be zero, right? Field will be zero. We'll be left with only a single charge, that's the minus q charge. We'll be left with a minus q charge only, and the field because of this minus q charge will be along this direction, right? Let's suppose the distance from the center to this point is actually r, right? Then the field at this point will be nothing, that will be kq upon r square. So this will be the net field at the center of this regular pentagon. We have four charges are placed at the four corners of regular pentagon, right? So this is how we can solve this question, right? Now, talking about the question number 11, right? Question number 11. At center of ring of charge Q is placed a charge Q, then find the tension in the ring, right? Then find the tension in the ring, right? You can see here we have this uh, ring here, right? We have this ring here, right? And at the center of this ring, there's a charge Q, right? And the charge on this ring is plus Q, right? Charge on this ring is plus Q like this, right? It's uniformly distributed charge on this ring, right? We have to find the tension within the ring. We have to find the tension within the ring. We know that at the center of the ring, the net field at the center of the ring will be zero, right? So E center will be equal to zero, right? Net field will be equal to zero, but there will be a tension within the ring because of this. The total force on this ring will be zero here, but there will be a tension within the ring, right? There will be a tension within the ring, right? There will be a tension within the ring, right? Let's suppose that let's cut this ring into two parts. Let's suppose this is half of the portion of this ring like this, right? Half of the portion of ring like this. Now you can see if the tension is T in this ring and this tension will be T in the entire ring, right? So the tension at this point will be tension at this point has to be along this direction, right? Has to be along this direction. Let's suppose that's T, and the tension at this point is also along this direction. Let's suppose that's T, right? So the charge Q is placed here, right? Now the force, let's suppose this net force because of this charge Q on this half ring is F, right? Then this F should be equal to 2 times the tension, right? Then only this half ring will remain in equilibrium, or the net force on this half ring will be equal to 0, right? So from here the tension will be nothing, it will be F by 2, right? It will be F by 2. Now we have to calculate the value of this F, right? The value of this F. The value of this F. So this F will be nothing, that will be the charge multiplied by the electric field at this point. The charge multiplied by the electric field. I can see here the electric field because of this ring, right? Because of this ring having the charge density lambda, we know it's equal to 2k lambda upon r, right? Sine theta over 2, right? Sine theta over 2, where theta is the angle subtended at the center of this thing, right? Now the angle here is 180 degree, right? So 180 upon 2 will be 90, or will be left with field equal to 2k lambda upon r, right? 2k lambda upon r, 2k lambda upon r, right? 2k lambda upon r. So the force here F will be equal to it will be Q multiplied by 2k lambda upon r, right? Now the tension here will be nothing, that will be 2k lambda 2k lambda upon r, right? 2k lambda q upon r multiplied by 2, right? So 2 and 2 will get cancelled. The net force here will be equal to, it will be q lambda upon 4 pi epsilon naught r, right? 4 pi epsilon naught r. So this will be the net tension within this ring. So the tension in this ring will be equal to q lambda upon 4 pi epsilon naught r. So this will be the tension within this ring, right? Now let's move on to the question number 12 and question number 13, right? You can see here in the question number 12 we have, which of the following is true for the figure showing electric lines, right? Which of the following is true for the figure showing electric field lines, right? The option A is that EA, it means the electric field at point A. So this is the point A here, right? This is the point A, and this is the point B here, right? The field at A is greater than field at B. That field at B is greater than field at A, right? And potential at A is greater than potential at B, and potential at B is greater than potential at A. We know that electric field is always given by its minus del V upon del R. Or we can say that field is directed along decreasing potential. Field is directed along decreasing potential, right? Field is directed along decreasing potential, right? Decreasing potential, right? So electric field is always directed along the decreasing potential, right? So you can see here, if this is the direction of the electric field lines, it means uh, if the potential at this point is VB and the potential at this point is VA, so it's along the direction of the decreasing potential. It means that VB must be greater than VA, right? So the potential at B will be greater than potential at A, right? Potential at B will be greater than the potential at A, and the density of the electric field lines is more here, right? So it means the electric field at point A will be greater than the electric field at point B. So there are two options, correct, right? Field at A will be greater than field at B, and the potential at B will be greater than the potential at A, right? So the option A and the option D are the correct options for this question, right? Now let's discuss the question number 13 here. An uncharged sphere of metal placed inside a charged parallel plate capacitor, right? So an uncharged sphere of metal placed inside a charged parallel plate capacitor. A charged parallel plate capacitor consists of two large parallel positively and uniformly charged plates, right? Which of the following figure correctly represents the electric lines of force, right? Where to tell which of the following will be the correct representation of the electric lines of force. So we have two plates here, right? Two plates of capacitors here, right? This is the positively charged plate, right? And this is the negatively charged place, right? Negatively charged place. We have placed a metallic sphere, right? Metallic sphere. We know that in case of metals, the electric field lines always fall normal to the metallic spheres, or the electric field lines do not penetrate the metallic sphere, right? Now you can see here there will be electric field, right? And this electric field will be falling normal on this metallic sphere, right? So it means that the case in which only the electric field lines are falling normal, it's this case, right? Here the field lines are falling normal to this metallic sphere. So this will be the correct representation, or this will be the correct representation of electric lines of force on this sphere, right? Option number C will be the correct option. Now let's discuss about the question number 14, right? Discussing the question number 14, right? The question number 14 says that n small drops of same size are charged to V volts, right? Each n small drops of same size are charged to V volts each. If they coalesce to form a single large drop, then its potential will be, right? So it means that we have n small drops, right? We have n small drops, each of, let's suppose, each of charge q and each of small radius r, right? Each of small radius r, right? These are n such drops. There are n such drops, right? Identical drops, each having charge small q, and small q, right? Small q, right? Now what happens is that these drops actually coalesce each other, right? They coalesce each other and to form a bigger drop. They form a bigger drop of radius r, right? They form a bigger drop of radius r. Let's suppose the potential on this bigger drop is v naught, right? Let's suppose the potential on this bigger drop is v naught, right? They coalesce to form a single large drop, then its potential will be, right? Now talking about this small drop, right? Talking about the small drop, right? Talking about the small drop, right? Talking about the small drop of radius r, the charge is q. The potential of this charge q will be nothing. It will be kq upon r, right? It's kq upon r. This will be the potential of this drop. Now, when all these n drops actually combine to form the large drop, the volume of all these drops will be equal to the volume of this large drop, or we can say the volume of this larger drop will be 4 by 3 pi capital R cube, right? That will be n times the volume of these drops, right? 4 by 3 pi R cube. So 4 by 3 pi will get cancelled. We'll be left with n will be here equal to the value of capital R here will be equal to n to the power 1 by 3 into R. So this will be the radius of the bigger drop, right? This will be the radius of the bigger drop. And the potential of the bigger drop will be nothing. We know once again that the total charge should also be conserved. So n times q will be the total charge on this bigger sphere, right? If the charge plus q is on this bigger sphere, so n times q will be the charge on this bigger drop, right? So the potential on this bigger drop will be nothing. That will be equal to kq upon the radius, right? Kq upon the radius. The q value is n times q upon the radius. That's r, right? That's r. The value of this radius r is given as, the value of this radius r is given as n to the power 1 by 3 into r, right? N to the power 1 by 3 into r. That's equal to n 1 minus 1 upon 3, right? Kq upon r, right? So this will be equal to n to the power 2 by 3 kq upon r, right? This will be the potential on the bigger drop, right? The potential on the bigger drop will be actually v naught. That will be equal to n to the power 2 by 3 times v, right? This will be the potential on a bigger drop, right? This will be the potential on a bigger drop. So the potential on a bigger drop will be v times n to the power 2 by 3, right? So the option D will be the correct option for this question, right? So option D will be the correct option for this question. Now let's move further, right? Let's move further. Question number 15, right? The question number 15 says that two identical particles of mass m, right? Two identical particles of mass m carry a charge q each, right? carry a charge q each. Initially, one is at rest in free space and the other is projected towards the first particle from a large distance with speed v, right? So we have two charges here, right? Two charges, each of charge q, right? Each of charge q. One charge is placed at a large distance, right? And it's projected with some speed at this infinite distance, right? Let's suppose the kinetic energy of this charge will be half mv square at this point, right? Because there is no force of interaction between these two charge particles at infinite distance, so the potential energy at infinite distance will be equal to zero, right? Once this charge q approaches this charge, right, approaches this charge, there will be a force of electrostatic repulsion between them, right? So after some time, at some point, the speed of this charge q will continuously decrease, and at this point p, right, at this point p, finally this charge stops, right? This charge q stops, right? This charge q stops. Let's suppose the maximum distance it approaches is the distance d, and this distance d is the distance of the closest approach. So at this distance of the closest approach, the total kinetic energy of this charge will be converted into the potential energy between these two charge systems, right? Or we can say that half mv square will be equal to the potential energy of these two systems at the closest approach. That will be kq square upon d, right? So the distance of closest approach for these two charges will be nothing. That will be equal to kq square upon 2 multiplied by mv square in the denominator, right? So this will be the distance of the closest approach for the two charges, right? 2 kq square upon mv square, right? Now let's talk about the question number 16, right? So the question number 16 says that in a certain region of space, the potential is given by, in a certain region of space, the potential is given by k multiplied by 2x square minus y square plus z square, right? So this is the potential given by k 2x square minus y square plus z square, right? This is the potential, right? The electric field at the point 1, 1, 1 has magnitude, right? We have to find the electric field because of this varying potential at the coordinate 1, comma 1, comma 1, right? We know the electric field relation between the electric field and the potential is nothing. Electric field is given as minus gradient of potential, right? Minus gradient of potential. Or we can write this as minus del upon del x I cap, right? Plus del upon del y j cap plus del upon del z k cap, right? Multiplied by this potential v, right? Now the potential v here is given as 2x square minus 5 square plus z square multiplied by k. So it means ex here will be equal to, it will be minus del v upon del x, right? Or ey will be here equal to minus del v upon del y, right? Ez will be here equal to minus del v upon del z, right? Now substituting the potential value of the potential in this equation, right? So minus del upon del x of v is equal to k times, it will be k times 2x square minus y square, right? Plus z square, right? So taking the derivative here at this point, it will be minus 2, it will be minus 4k, right? Minus 4k into x, right? Similarly, we have the value of ey equal to, ey will be equal to plus 4k, right, into y, right? 4k into y. So it will be plus not 4k plus 2k, right? Plus 2k into y, right? Plus 2k into y. That will be ey. And ez will be equal to 2k into z, right? 2k into z, right? With a negative sign, right? Minus 2k into z. Now at the points 1, comma 1, we'll have ex equal to, we'll have ex equal to minus 4k, right? And ey equal to 2k, right? And ez equal to minus 2k, right? So the magnitude of the net field here in this case will be under root of ex square plus ey square plus ez square. It will be 4k whole square plus 2k whole square plus 2k whole square, right? So it will be 16 plus 4, it will be 20, and into 4 will be 24, right? It will be k root 24, right? Or we can write it equal to, so k root 24 can be written equal to 2k root 6, right? 2k root 6. So this will be the net electric field. This will be the net electric field at this point 1, comma 1, comma 1. So 2k root 6, right? 2k root 6 will be the correct option. That's option number B, right? 2k root 6 will be the net electric field at this point 1, comma 1, comma 1, right? Now let's discuss this last question right here. The question number 17 says the figure shows the electric field lines in the vicinity of two charges, right? The figure shows the electric field lines in the vicinity of two charges, where two charges here Q1 and the charge Q2 here, right? The charge Q2 here, right? Which one of the following statements concerning this situation is true, right? Now we can see here there are certain electric field lines which are originating from the Q1 charge and are terminating on the Q2 charge, right? So the option number one is that Q1 is negative, Q2 and Q2 is positive. You can see here the electric field lines originate from the positive charge and terminate on the negative charge. It means that Q1 charge has to be a positive charge and Q2 charge has to be a negative charge, right? It has to be a negative charge, right? So Q1 cannot be negative charge. It's incorrect option, right? Q1 is a positive charge, that has to be a positive charge. Let's talk about the option C. Q1 and Q2 both have the same sign of charge, so they cannot have the same sign of the charge, right? Then for same sign of the charge, the field lines will be a repulsive field lines, right? But the field lines are terminating on Q2 and originating from Q1, so these charges cannot be same as well, right? So option C is also incorrect option, right? Now talking about the option D, the electric field is strongest midway between the charges, right? Now you can see here in the middle point, the density of the electric field is less and the density at this point is more. So electric field will be actually more at this point, right? At this point, not at the middle, right? E1 will be greater than E2, right? At the middle, the electric field lines will not be strongest midway because the field density is less at the midpoint and field density is more. Field line density is actually more near the charge Q1, right? Now let's focus on this option number B. The option number B says that the magnitude of the ratio Q2 upon Q1 is less than 1, right? Q2 upon Q1 is less than 1, right? I can see here the number of field lines terminating on the charge Q2, number of field lines terminating on the charge Q will depend upon the magnitude of charge Q, right? If the magnitude of charge Q is greater, then the more number of field lines will terminate on the charge Q, right? But you can see here there are certain electric field lines originating from Q1, but all the field lines are not terminating on Q2, right? It means that if all the field lines are not terminating on Q2, it means that the charge of Q2 should be less than equal to the charge of Q1, right? Or the magnitude of Q2 should be less than the Q1, right? From here we can conclude that Q2 upon Q1 ratio has to be equal to less than 1, right? Has to be equal to less than 1. So the correct option here for this question will be option number B. Q2 should be less than Q1. But that will be the correct option for this question, right? That will be the correct option for this question, right? So that's it for today, right? That's it for today. We'll be meeting in the next lecture. We'll be stopping here, right? We'll be discussing the part second of this electrostatics portion, right, in the next lecture. So see you soon. Till then, take care and goodbye.